Welcome back to Very Ordinary Differential Equations. In this lecture, we continue our study of second-order linear equations, specifically constant coefficient homogeneous equations where the characteristic polynomial has two distinct roots. So, we have seen already that in order to find all solutions to a homogeneous linear second-order differential equation of the standard form y double prime plus p of xy prime plus q of xy equals 0, we need only find two different solutions and show they are linearly independent. Now what we're going to do is study how can you actually find those two solutions to begin with. We begin with the simplest possible scenario. P of x and q of x are just constants. So we have y double prime plus a constant times y prime plus another constant times y equals 0. In general, however, we're going to go ahead and put a constant in front of y double prime as well. A y double prime plus by prime plus cy equals 0. If a were 0, then we would actually have a first order equation and we already know how to solve that. And if a isn't 0, it's permissible to divide by it, in which case we would have this simpler form, y double prime plus some constant times y prime plus some constant times y. In other words, there's not really a problem in going ahead and having a non-zero coefficient in front of y double prime. It is equivalent to a standard form second-order linear differential equation. So we're going to go ahead and put a constant there. It just makes it a little easier to work with later on. Now let's suppose that y happens to be an exponential function, e to some number r times x. Then y double prime is r squared e to the rx, and y prime is r e to the rx. So, if y happens to be one of these exponentials e to the rx, if I plug it into the differential equation, ay double prime plus by prime plus cy equals 0, we would get ar squared e to the rx plus br e to the rx plus c e to the rx equals 0. So for our second-order linear differential equation, homogeneous, constant coefficients, in other words, ay double prime plus by prime plus cy equals 0, we're just checking, hey, maybe an exponential e to the rx is a solution. And we ended up checking maybe this is true. If y is e to the rx, then this works out to be ar squared e to the rx plus br e to the rx plus c e to the rx equals 0. Now we can factor an e to the rx out of every term. And since e to the rx is not 0, we can instead ask, is ar squared plus br plus c equal to 0? So from the original equation, ay double prime plus by prime plus cy equals 0, this quadratic polynomial that arose, ar squared plus br plus c, is called the characteristic polynomial, and ar squared plus br plus c equals 0 is called the characteristic equation of the differential equation. So for a linear second-order homogeneous differential equation with constant coefficients, we've determined it's actually solved by the exponential function e to the rx if and only if r is a root of the characteristic polynomial ar squared plus br plus c equals 0. Notice, going from the second-order differential equation with constant coefficients to the characteristic polynomial is pretty straightforward. Y double prime is equivalent to r squared, y prime is replaced with r, and y just goes to 1. This is what happens when you make the assumption that y is this exponential function here and compute these second and first derivatives and then cancel out the e to the rx from every term. Now we happen to know that if we can find two solutions that are linearly independent, we have found a fundamental set of solutions to the original differential equation. If r1 is not the same as r2, it's easy to show that two different exponentials, okay, so e to one power of x and e to a different power of x, those are going to be linearly independent. Computing the Wronskian is very straightforward, and you can see it's never 0 under the assumption that those two exponents are different. Therefore, if this characteristic equation has two distinct real numbers, r1 and r2, that are roots, then e to the r1x and e to the r2x both solve this differential equation. Since those are linearly independent, we will have found a fundamental set of solutions. So let's address that claim from before that if r1 isn't r2, then e to the r1x and e to the r2x are in fact linearly independent. Well, let's go ahead and set y1 is e to the r1x and y2 is e to the r2x and compute that Wronskian. It's pretty straightforward. So we need to compute y1, y2 prime minus y1 prime, y2. So y2 prime just brings out a factor of r2. y1 prime brings out a factor of r1. But in both cases, I get this e to the r1x times e to the r2x. So I factor that out, e to the r1 plus r2x, leaving behind r2 minus r1. And this exponential can never be 0. And if we assume that r2 and r1 are not equal to each other, this constant isn't 0 either. So if the characteristic equation ar squared plus br plus c equals 0 has two real roots that are different from one another, r1 and r2 are not the same number, but they're both roots of this quadratic, then e to the r1x and e to the r2x both solve the differential equation and are linearly independent, therefore they form a fundamental set of solutions. As a first example, let's find a fundamental set of solutions to 2y double prime plus 5y prime minus 3y equals 0. Well, the characteristic equation is just 2r squared plus 5r minus 3 equals 0. If we don't see how to factor this quadratic, well, it is a quadratic function, we can always use the quadratic formula. So r is a root of the characteristic polynomial exactly when r is -5 plus or minus 5 squared minus 4 times -3 times 2, all divided by 2 times 2. This works out to be -5 plus or minus root 49 over 4, which works out to +1/2 and -3. Therefore, since we have two roots of the characteristic equation that are not the same number, e to the 1/2 x and e to the minus 3x form a fundamental set of solutions to the differential equation. As a second example, let's solve the initial value problem. Y double prime plus y prime minus y equals 0, where y of 0 is 0 and y prime of 0 is 2. Well, again, we're going to make the characteristic equation r squared plus r minus 1 is 0. This does have two real roots, which we find from the quadratic formula to be -1 plus root 5 over 2 and -1 minus root 5 over 2. So a fundamental set of solutions is given by e to the r1x and e to the r2x, where the values of r1 and r2 have been given above. So any solution must be of the form some constant times e to the r1x plus some other constant times e to the r2x. Having determined that any solution to the differential equation is of this form, c1 e to the r1x plus c2 e to the r2x, where we know explicitly what those values r1 and r2 are, we can start working with our initial values. Starting with y of 0 is 0. So if I let x equal 0, both of these exponentials become 1, and you just get c1 plus c2, but that's y of 0, which was given to be 0. So c1 plus c2 must be 0. Computing derivatives is pretty straightforward. Okay, the derivative of y is going to be r1 c1 e to the r1x and r2 c2 e to the r2x. Plugging in x equals 0 makes the exponentials vanish, and you get r1 c1 plus r2 c2 must be 2. Now the first equation, c1 plus c2 equals 0, tells me that c2 must be negative c1. If I plug that into the second equation, we get 2 must be r1 c1 minus c1 times r2, which I factor out the c1 and get 2 is equal to r1 minus r2 times c1. So we have found that solutions must be of this form, where r1 and r2 are explicitly known. c2 must be the opposite of c1, and we also have this relation here, that 2 must be r1 minus r2 times c1. Now r1 minus r2 can actually be computed. If I compute this value of r1 minus this value of r2, notice that your -1/2 will cancel, and I'll have root 5 over 2 minus negative root 5 over 2, and that'll just be root 5. So r1 minus r2 is just root 5. That allows me to solve for c1 is 2 root 5 over 5, and c2 must therefore be the opposite of that, -2 root 5 over 5. So our exact solution has been found to be 2 root 5 over 5 times e to the r1x minus e to the r2x. As a third example, let's find all possible solutions y double prime equals 4y with the initial condition y of 0 equals 10. So we're going to standardize the form so that we have y double prime and then some constant times y prime, where that constant is 0, there is no y prime term, minus 4y equals 0. Now it looks like a homogeneous linear second order differential equation with constant coefficients. The characteristic equation is given by r squared minus 4 equals 0, which has two roots, plus or minus 2. So a fundamental set of solutions is given by e to the 2x and e to the minus 2x. Therefore, any possible solution is of the form c1 e to the 2x plus c2 e to the minus 2x. So we've determined that all possible solutions must look like some constant times e to the 2x plus another constant times e to the minus 2x. Our initial value y of 0 equals 10 allows us to conclude that c1 plus c2 must be 10. But that's the only information we have, so we can't actually solve for what c1 and c2 are exactly. But we can say, for example, that c2 must be 10 minus c1. That allows us to write it in the form c1 e to the 2x plus 10 minus c1 e to the minus 2x. In other words, there's really only a single unknown left. Okay. With only one constant unknown, the subscript is a little unnecessary. So we can simply write that y is some constant e to the 2x plus 10 minus that constant e to the minus 2x. We don't have an exact solution yet. We didn't have enough information to begin with, but we've narrowed it down a bit. Altogether, what have we learned? Suppose we have a homogeneous linear second-order differential equation with constant coefficients. In other words, ay double prime plus by prime plus cy equals 0. We form the characteristic polynomial ar squared plus br plus c equals 0. If that has two distinct real roots, r1 and r2, then a fundamental set of solutions is given by e to the r1x, e to the r2x. But what if the characteristic polynomial didn't have two real roots? What if it only had one real root? Or what if it didn't have real roots at all? Clearly, we have some more work to do.